second session of gate physics program. And last class we just looked at the definition of dot product and cross product, and then I told you I will continue with gradient, divergence and curl today's class. And in terms of defining the length of the vector, I forgot to mention about this. So if you have a vector, the dot product of itself will give you the magnitude in terms of components, which is a dot a vector is modulus of a square or simply a square. So what will this be equal to in terms of components? This will be equal to ax square plus ay square plus az square. Then the magnitude of the given vector A, denoted by A without a vector symbol, will be square root of ax square plus ay square plus az square. This for completeness I wanted to mention. Suppose one has a function f of a single variable x, then what does df by dx signify? If I have a function f which is a function of single variable x, and then what does df by dx signify? So it tells you how the function f changes rapidly when we go from x to dx. Whenever there is an infinitesimal change from x by an amount dx, then df is df by dx into dx. And what is df by dx? It's essentially slope of the graph between f of x versus x. So this denotes the slope of f of x versus x graph. Now this is for a single variable, a scalar function f of x. Now let's consider a case, say for example the temperature in this room. So how many variables do we require in this case? We require 3 variables. So if I want to find the temperature, how the temperature is varying at different positions in this room, then we require how many variables to denote? We require 3 variables. So T is essentially a function of x, y and z. Since temperature is a scalar, so what we have is a scalar function. Now, is it possible to extend the definition of the slope in this case also? Though it might look difficult, using the definition of partial derivatives, it is not that difficult. So dt is dou t by dou x into dx plus dou t by dou y into dy plus dou t by dou z into dz. Obviously, when one is finding the derivative, so here it's partial derivative, so that means when you are evaluating derivative with respect to x, y and z is kept constant. In this case, x and z are kept constant, as well as here x and y are kept constant. Now, in mechanics, so whenever we have a frame of reference, if I have any point P in space in Cartesian coordinates, how can we denote them? So this is x cap, y cap and z cap. And how do I denote the point P in terms of Cartesian coordinates? How do we denote? We denote it in terms of components x, y, z, so the point P. So if you take this point as your origin as a reference, if you want to know the vector which is going along this, which is connecting origin and the point P, the vector connecting these 2 points are essentially called as the position vector. So that tells you the position where you are trying to locate. So what is the symbol we use? This is denoted as R vector, and the unit vector which goes along with it, so which is meaningful by the drawing which I have drawn, because the radial vector is moving out. So if x, y, z is the component of this vector R, then what will be the expression for R vector in terms of x cap, y cap and z cap? So that will be R vector is x into x cap plus y into y cap plus z into z cap. And what will be the magnitude? That will be equal to R is square root of x square plus y square plus z square. So now, if you consider an infinitesimal displacement from this point x, y, z to a nearby point which is x plus dx, y plus dy and z plus dz, then you can find that infinitesimal displacement and denote it as a dr vector. So we are moving from a point x, y, z to a point which is infinitesimally nearby, which has a coordinate of this form. And what will be the displaced vectors? Components will be, so in the same way, this will be dx x cap plus dy y cap plus dz z cap. So now, using the definition of the dot product and dr vector, we can rewrite dt in this way. Dot dx x cap plus dy y cap plus dz z cap. Are these definition equivalent? This and this? Are they equivalent? Yes. So now, here we can write this as delta t dot dr vector. So what is delta here in the definition which I have written? So dt is delta t dot dr vector. So here del formally by definition is called a del operator, which is of the form x cap dou by dou x plus y cap dou by dou y, z cap dou by dou z. Note that this is a vector operator. It acts on a scalar function which is t of, in this case, the temperature x, y, z. So which is a scalar function, and it gives you delta of t. And if you remember from dot product definition, if delta t represents a vector, what is this dot product geometrically represent? This is equivalent to modulus of del t. And some textbooks you will see delta with a vector notation. So if you wish, you can put that way, or otherwise without. So by definition, delta is a vector operator. For consistency, we will maintain the arrow. So what is this equal to? Is equal to, if it is a dot product of delta t into dr, so that's what is going to tell you the infinitesimal change in the temperature function t, which is function of x, y, z, and this is equal to delta t modulus of delta t into modulus of delta r into cos theta. So for a fixed magnitude of the displacement vector, if you fix the magnitude of this, then what we can infer? When will the function t x comma y comma z will be, or dt will be maximum? When theta equal to 0. So when theta equal to 0, for a fixed value of this, dt will be maximum. So that essentially means delta of t as a vector, the direction of which tells you where the function t is becoming maximum. So that denotes the maximal direction, or it gives you an analogous of one-dimensional slope which we had. Now you have a three-dimensional case. And what does the magnitude represent? What does the magnitude represent? So the gradient delta t gives, the vector gives you the maximum direction, and the magnitude of delta t gives you, what does it give? The magnitude of delta of t. So that gives you the slope or the change. So that gives you the rate of increase or the rate of change, which is slope along the maximal direction. So what we intended to start out off with, I have a single function of variable, I have a definition of slope. Is it possible to extend it to 3 dimensions?